Okay, for the first question, they ask us to calculate the initial value of I. So, first thing first, it is easy to us to find the I by using just the Ohm's law formula. But first thing first, we need to find the R equivalent. So we need to first combine the 30 ohm and 6 ohm resistor in parallel, which means that R equivalent is equal to R1 R2 over R1 plus R2. So we can get here 30 times 6 over 30 plus 6. So we can get 5 ohm. After that, we need to use the voltage division to find the voltage drop across the parallel resistor. So V is equal to 5 over 5 times 3 times 120. So this 120 we can find in the picture, the value given by the power source is 120 volt. So we calculate this and then we will get 75 volt. So just after that, we can use the Ohm's law to find the current. So we calculate and then we will get negative 12.5 ampere. That's for the first question. So move on to the next question. So the next question, calculate the initial energy stored in the indicator. So for the second question, we need to simply just using the formula of omega naught is equal to 1 over 2 L I squared. So what is L? L is for the inductance. So formula 1 over 2 times inductance 8 to the power 8 times 10 to the power of negative 3 times 12.5 squared. This I is from the earlier that we got from the question 1, negative 10.5. So we put in here 12.5 squared. So and finally we will get this 6.25 times 10 to the power of negative 3 joule, or we can convert it also to be 625 millijoule. So next we move on to the third question. So for the third question, the question asks that what is the time constant of the circuit for t is more than 0. So to find the time constant, we need to find the equivalent resistance seen by the indicator for t is more than 0. When the switch open, only 2 ohm resistor remain connected to the inductor. Thus, we can apply the formula of torque is equal to L over R. So just input the formula, input all the value 8 times 10 to the power of negative 3 over 2 resistor 2 ohm. So we can get the value of 4 times 10 to the power of negative 3 second, or you can convert also to 4 milliseconds. So next, for the fourth question, what is the numerical expression for IT for t is more than or equal to 0? So in the general, IT in the for the answer is I times exponent to the power of negative 3 over tau. So just simply put all the value that we get from the earlier question. So what is I? I is negative 12.5. Exponent remain the same. Then we can get negative 250 t. So where do we get negative 250 t? From the third question, 1 over t is equal to 1 over 4 times 10 to the power of negative 3. Then we will simply get 250. So just put back the value into the formula so we can get negative 250. So the full answer is negative 12.5 exponent to the power of negative 250 ampere when the condition is t is more than or equal to 0. So last but not least, the final question, it asks us to what the percentage of the initial energy stored has been dissipated in the 2 ohm resistor 5 millisecond after the switch has been opened. Okay, so first thing first, we need to use the formula of 1 over 2 Li squared. So just input all the formula back all the values back into this formula. So 1 over 2 times 8 times 10 to the power of negative 3. And then what is I? What is I? We get from the earlier here, I, this one, negative 12.5 exponent to the power of negative 250t. So just put back the formula into here. Okay? So to the power of 2. So, and then we get this, before this, the earlier formula is negative 250t. But as the question given, in 5 millisecond after the switch has been opened. So we just can convert the 5 millisecond, the time given, we just convert it. 5 millisecond is equal to 0.005 second. Just put into the formula negative 250 times 0.005. So the answer we will get is 0.0513 joule, or we can convert it into 51.3 millijoule. After that, we can calculate the energy dissipated. So just the energy that we get earlier is 625 millijoule here. Yes, here in question number 2, 625 millijoule. So after that, just minus 625 millijoule minus the 51.3 millijoule. So we can get 573.7 millijoule. So that is the amount of energy dissipated. But the question asks for the percentage. So easy, just put 573.7 millijoule over 625 millijoule times 100%. We will got the final answer of 91.792%, or 91.79%, or 91.8%. So that's all for the calculation. Alright, just now I have presented to all of you, I have explained to all of you about the calculation that we use in this circuit. So now I will explain to all of you about the circuit simulation in the multi-sim software. So now you can see that of course we have this power source, and then we have 1, 2, 3 and 4 resistor, and then we have this one capacitor, and we have, I put this ammeter for us to see the amount of current that flow, and then I put this oscilloscope for us to see the waveform, and of course we have ground. So yes, of course this circuit was from the question. And then so let's see the waveform. Alright, so let's play. So now when the switch is closed, there is no change in the inductor, which means that inductor now resists the change in the current flow. So as you can see also here, when the switch is closed, the amount of current is negative 12.5, no change, and here there is no amount of voltage applied. But what happened if we open the switch? Let's see. Here, see here. Yes. When we open the switch, there is change in the current in a click of time. So here, the energy is being used up by this indicator. So after that, we can see that the graph change gradually to 0. Gradually, you see here. Okay, you see this ammeter. See this graph. This graph shows that maybe the waveform is 0, but this ammeter shows that it will continue get up, step up back from exponentially negative, get back up gradually to 0. Let's see. See? Alright, let's pause this one. Alright, so when the waveform is gradually to 0, which means that there is no current flow through the indicator. Yes, of course, because the current is gradually turned to 0. But what happened when we close back the switch? Open, close, open, close, open, and close. Alright, pause. Alright, so as you can see here, this is negative exponential and positive exponential waveform. Alright, this negative exponential waveform are called as natural response. Again, this part is called natural response. Meanwhile, this upper part is called as step response. So what is this natural step response? What is this? So natural response occur when the inductor here, ongoing the energy decay. So what does this also mean? So when the inductor ongoing the energy decay, okay, when the switch is open here, when the switch open, this is the switch close. The upper part is when the switch close, the lower part is when the switch is open. When the switch is open, the inductor's energy is being used up, and also as all of you can see, the waveform change very fast. So why does it happen? Why does not the waveform change gradually low, and then gradually increase back, and then gradually increase, and then gradually change back to 0? So this is because the values in the circuit are very small, relatively small. So that's why the change occur very fast. Let me show again. Alright, open, close, open, close, open, and close. So as you can see, the waveform here change very fast. Because of what? Because the values in the circuit are relatively small. So I think that's all for me. I hope you understand about the simulation of the circuit that I explained just now.